Okay, so for this PowerPoint, the purpose of it is to show you what you need to do as part of the Extended Practical Investigation SAC. I'm going to be going over what you'll be doing and how you're going to be doing it. And what you're going to be doing is basically writing a scientific report. It can be in the form of a report or a poster. In previous years, it had to be in the form of a poster, but now for this year, with the changes because of COVID, it can be in the form of just a science report. So I'm going to go through what's involved with that. Now, I'm going to upload this. It's part of the rubric. It'll be available on the Compass or Teams. I'll tell you which on the day. But it's going to go through everything that needs to be in your science report. So if you don't need to keep coming back to this video to see the rubric, you can just access it wherever I upload it. So I'm just going to go through all the different parts of a science report, then go through an example one from a previous year that I thought was pretty good. And then towards the end, I'm just going to show you a bit about creating graphs in Excel, because that might be something you want to do as part of your report. So you're going to have an aim at the beginning that describes what was to be investigated during the experiment, and you can see that for the rubric there are a very high, medium, low, very low, and just not shown. And you can see that some of them, because the first one is out of 3, you either get a very high, you get a medium, or you get a very low. So normally some of them are out of 5. You can see the next one down is out of 5, but some of them are going to have gaps missing just because they don't need to be as detailed. The points that are allocated for each one basically shows you how much detail you should be going into, and how many ways there are for you to lose marks. So just a bit of a heads up, normally when you do an experiment, it's often wise to write the aim at towards the very end, because once you've written the method and once you've written out your results, then it's easy for you to know what the experiment's about. If you're trying to write about what the experiment actually is before you actually have gone through it, then you might not know enough detail to write a good aim. So it's just an idea. You don't have to do it, but it's just a common way for people to write their reports. Aim and conclusion are normally written towards the end because, well, by that point you know everything you're going to know about the experiment. You'll need to talk about the relevant background physics. Now, once you've watched through the video, you'll have an idea of what's happening. A big concept, just to give you a heads up, for this experiment is going to be based around torque. So we looked at torque back when we were looking at stuff to do with motors, and that's going to be an idea that you're going to need to write about and have a think about. Again, you might want to put off writing about those physics parts until you actually have your method and your results and maybe a bit of your discussion in place, because by then you'll know what's happening and it'll just be about explaining what's happening. So you don't have to write your report in order. So this is a section that's probably better off doing a bit later. You then have your methodology, which is, I've been called it a method, but methodology is what we prefer to talk about. You list the steps that you use, so that's a no-brainer. You need to make it clear that in a way that could be followed by someone repeating the experiment, and I'll give you an example later on so you know what you need to do. You need to describe the variables. So this is where the theory that we've looked at is going to start coming in. You need to list the variables involved in the experiment, and you need to classify them according to whether they are an independent variable, a dependent variable, or a controlled variable. So because this experiment involves 2 parts, the first part is you have one ruler and you change how much of it's over the edge and then see how far it goes. The second part is you use different rulers, but the only way for you to make comparisons between the different types of rulers is based off what percentage of the ruler is over the edge. So for example, if I've got a meter long ruler and half of it's over the edge, I can compare that with a 30 centimeter ruler where half of it's over the edge as well, even though in the first case 50 centimeters is over the edge and in the second case 15 centimeters is over the edge. The same percentage of the ruler is going to be over the edge for the second part of the ruler, and if that's the case, I can compare what effect the length of the ruler has on the results. If I was to just say 15 centimeters of one and 15 centimeters in another, I don't think that's a fair comparison to be made, given that the rulers are of different lengths. So one of the things you're going to be dealing with that's not in your data sheet but you're going to have to account for in your experiment is the percentage of the ruler that's hanging over the edge. You can only compare them if you've got the same percentage of one ruler as you have for another ruler hanging over the edge. So just keep that in mind, that's going to be the second part of the experiment, and that's something you're just going to need to calculate, something you're going to need to think about when you're classifying your variables, because which one's independent, which one's dependent, and what's controlled, those might change from the first part of the experiment to the second one. Then you include a picture of the setup, and it needs to just clearly show what's going on. Helps people who are looking at your report visualize what's happening, so it's always a good thing to include. You need to identify any risks and talk about ways you would reduce those. And if you think about this experiment, if you've seen the video of what's happening so far, then you can probably think of a few risks that would be involved if you were doing this with like 2 people, for example, or even if one person was just doing it in a room full of other people. So that's something you need to include. Your results. You need to be creating a graph of your data. It needs to have labels on its axis. It needs to have an appropriate title, and it needs to be presented in a way that is easy to read. That last point is basically a free point if you're making a decent enough graph. I just don't like it when people make graphs that don't look good in like a basic functional sense. So just as long as your graph is like a graph, really a decent enough one, you'll get that last point about logical, easy to read. It's basically a free point. You need to include uncertainty bars on your graph, and when you create your graph, you can either do it by hand and then put it into your report, or you can use some kind of program and like Excel to do that. I'm going to go through at the end of this how you'd create the graph and create uncertainty bars using Excel. So if you want to go about it that way, that's something I'm going to talk about later on. You need to include some sample data. You don't even need to include all your data because, well, your graph basically represents your data. You're going to be doing some sample calculations. They're going to involve things like finding the average distance that the ruler traveled for a certain percentage of its length of the edge. You'll need to do some averaging for this, these results. And you're also going to need to talk about calculating percentages, which are easy enough calculations to do. If you've got a ruler that's 30 centimeters long and 15 centimeters are over the edge, hey, 50% of the ruler's over the edge. Those sorts of calculations are something you're going to need to do. You also need to include uncertainty calculations. Not every single one that you do, but like if you do one type of calculation, and then you do it like 10 more times or whatever, you only need to include one example of you doing it, showing that you know the steps to do that uncertainty calculation. Include that in your report, and then you can just say, I did it this way, and then I did it 10 more times doing the same steps, getting my other uncertainties, which would be represented on your graph. They don't need to be all listed in a table or anything. You have your discussion where you talk about patterns in your results. So if you've got your graphs up for your data, you should be able to look at them and say, well, here's what's happening in my graph. Here's the pattern that is kind of being shown visually. You need to talk about how those patterns are tied in with the relevant physics. So again, before you do that, you're going to need to know what the relevant physics are. This would be a good time to go back and do a bit of research into what the physics is. You might need to do research as part of this. I don't expect that you'll be able to look at this and go, bang, here's what's involved, here's what I'm going to have to write about. You might need to use your textbook or do some Googling, or just look into general physics stuff that's involved around talk. And that's what you're going to be writing about and trying to explain your results in terms of that physics. You want to talk about the limitations of the experiment, things that prevent you from maybe generalizing your results as much as you would like to. So just think about, well, what's a problem with my experiment? If I was to do it again in the future, how could I try and work around this problem? Something like that. There's one kind of obvious one that I'm not going to go into, I won't give it away, but you think about the experiment and the conclusions you draw from it, and what's one thing preventing you from drawing a very specific conclusion. But whatever, that's up to you. And finally, you end with a conclusion. So for this, it says for the first one, reference was made to the aim in summarizing what the outcomes of the experiment were. Like I said before, I often recommend that people write the aim and the conclusion. Conclusion obviously goes at the end, but because the conclusion involves referring to the aim when you summarize what happened, so if your aim is to find how high you could throw a bowl, your conclusion would be like, in terms of how high I could throw a bowl, it was this high, something like that. You go back to your aim and basically say, here's what I was trying to find, and here's what I found. So that's what the conclusions involves, and like I said, very closely tied in with what your aim is, so it's often a good idea to write them simultaneously. Here's a report from a previous year. It is written by Anonymous, in case you knows that, on the top left. I don't expect you to be able to read this. I'm going to upload a copy of this to Compass so that if you want to actually have a read through and see what's involved, you can do that. I would recommend doing it. It's for a different experiment than the one you are going to be doing. So you can't really draw from the physics here in terms of explaining your experiment, but it gives you a good idea of everything that's needed. It starts out with an introduction, which kind of is put first, talking about the physics that were involved in the experiment. So going into that in a lot of detail, you can see an aim down below that. You've got your variables, you've got methodology written out, the method for the first part of the experiment, then the method for the second part of the experiment. There's a picture drawn. There's a table of, not a table of data. There's a few different risks as well as ways to manage them. And then you've got a table of data which probably has more data than it needs to. It doesn't have to have all the data that you generate or data that you got from the experiment. So this one kind of went overboard, but you can see that there are uncertainties written on there, which is good. There's the table of data below that for the second part of the experiment. Down the bottom, you've got sample calculations. So for this one, it was basically saying, here's how I calculated, what was that first one? Calculated rebound percentage. And then he did some uncertainty calculations next to that. Up the top of the third column, you've got a few more calculations. And like I said before, it's a sample calculation. Here's one calculation that represents a few different calculations that I did, because I did them all in the same steps using the same process, so I only need to write down what my process was once. It's got the graphs. They've got trend lines on them, lines showing what's going on in the graph, and that's something you should just be including in your graph. I don't think that's in the rubric because I've put it. Maybe that's something I need to amend, but you should just have a trend line on your graph. I'm going to talk about how you put them on using Excel later on. And it might be hard to see, but there are uncertainty bars on the graph as well. So those are well put together graphs. Got their axes labeled, clear to read. It's got a nice title that talks about what's going on in the experiment. And hopefully you can see that the titles on the graphs are reasonably detailed. It's not just height versus height. It's not just one axis label versus the other axis label. I hope not. I can't read that as well as I could. Maybe it is saying that, but whatever. You want to give your graph kind of a title that says Y variable versus X variable, but you want to write it in a way that conveys what's being done in the experiment, what's being done to generate those sets of data. So for the top one, it says height of the rebound versus the height of the drop. He dropped the ball from a certain height and saw how much it rebounded. And so the title of the graph should refer to how the graph is showing on the vertical axis the rebound height, and on the horizontal axis the drop height. And it should just make it clear that that's what was actually happening in the experiment. You've got your discussion, which just basically talks about the results. You can have a read of the one that was put up here, which will be, like I said again, on Compass, but it basically just says, here are the patterns that I can see from my graph. Here's what happens as I change this one variable. Here's what happens as I change this other variable. And then here's an attempt, a big slab of paragraph, an attempt to explain that in terms of the relevant physics. So that's just what's involved in the discussion, and then ending with the conclusion, which I've talked about a bit already. So yeah, that's just what's involved in the post. So the next thing I'm going to do is I'm just going to go through what's involved in creating all the things that you need using an Excel document. If you're adamant about not using Excel for the purposes of this report, you don't really have to worry about the next part, but I'm just throwing it on here because it makes things a lot easier if you don't want to draw it by hand. So basically I've just invented some data points. I've got my X points on my left, I've got my Y points on the right. Start by highlighting all those. I go up to insert, and then I click on that little button that is there. So then I select the scatter plot option, click on that, and that's going to bring me up a graph showing my scatter plot. What I want to do, which I'm not going to do for this just to save a bit of time, is I'm going to click on that little cross button and bring up the axes titles option. If I click on that, I suddenly have titles on my horizontal and vertical axis, which I'd want to label. That's just part of making the graph, but to speed things along, I didn't do that here, but you do have to do it as part of your experiment. There's a little trend line button down the bottom there, and if I click on that, it applies a line of best fit. and you can see that that is about in the middle of all the point distribution, which is the way I told you lines of best fit need to be put on. It's not trying to pass through as many points as possible, it's trying to put on a line there that best represents the data that is there. What do I do next? So if I click on that, and I'm guessing my face might be covering up some options, so I might need to move the camera box around a bit. I click on the More Options button for my trend line, and this little sidebar is going to pop up. Now currently it's set to linear, it's a straight line. If you don't think that you're generating linear data, if you think your data might be some other form, if it might be exponential or logarithmic or a polynomial like a squared, for example, I think I've chosen a polynomial for this one. If you think it's a squared then kind of function, then you could put on polynomial order of 2, so the power would be 2 for that one. So that's like an x squared kind of function. And then you can see on the graph that there's that second line, and it's no longer linear. The linear one stays on. If I click on the linear one and press the delete button, it deletes the linear graph. So if I don't want that there, if I don't think my relationship's linear, then I can just delete that and leave behind my quadratic graph. You might look at this and think that, well, the quadratic one seems to fit a bit better than the linear one did. It seems like it's going closer to the points. That's true, but when I generated the data just by writing in numbers, I tried to go up by roughly 10 each time. I decided to throw it off so the points would not form a straight line. So linear fits would be reasonable in this situation, even though the other ones do seem to fit. Like the quadratic one does seem to fit a bit because it's going up in increasing size steps each time. Maybe a quadratic one would be better. Maybe. Either way, that's just how I get my line of best fit. The other thing you're going to need are uncertainty bars, or error bars as they're called on here. So we click back to that green cross and we select the error bars option. Now, if I click those, they get put on my graph. I select the More Options button because that's what's going to help me out. And then there's that little menu up the top. And if you click on that, you can see that there are, there's a bunch of options. The only two that really concern you are Series 1 Y error bars and Series 1 X error bars. Your vertical error bars going up and your horizontal error bars going across. So I think I start by selecting the Y error bars. No, start by selecting the horizontal ones. You can see it says horizontal below those. It's got to be on the graphs, like 3 bars option for this to work, but you can see that just above where my face is on the video, I've selected the option that says fixed value, and I've set that to 0.5, which tells me that each point on my data set is going to have a horizontal error bar that goes 0.5 to the left and goes 0.5 to the right. You can see that like the one at 1 goes down to 0.5 and goes up to 1.5. That's the same for all my error bars. So I select that option if I want to have error bars across all my points that are exactly the same value, and that's just how I would get those error bars on. Then what I've done is I've switched across to the vertical error bars, and I've also added on a new column to my data. So you can see that I've got 1, 2, 4, 5 there as well. And those numbers that I've put on there are going to represent my vertical uncertainties. They're going to be different from one point to the next. The first point has an uncertainty of plus or minus 1. The second one has an uncertainty of plus or minus 2. Third one is an uncertainty of plus or minus 4, and so on. So they're not going to be fixed. It's not going to be the case that each point has the same uncertainty this time. And so I'm going to pick a different option because I've got those varying uncertainties from one point to another. My face is covering this up at the moment. I'll see if I can move this in a bit once I've got this all saved. But in case I can't move my face from the screen, down the bottom of that error amounts little part on the sidebar, I picked the custom button, which is going to allow me to make the error bars different from one point to the next. I go to the first thing in the little menu that popped up. I delete number 1, but I leave the equals sign, and then I highlight all my data. So the positive errors, how much I want my error bars to go up from the points, I'm just going to get those by selecting the uncertainty numbers that I wrote like in my data. So I just highlight all those. Then I go down to the negative error value. I delete the little 1 in the brackets and leave the equal sign. I do the same thing and I highlight my data. So I've got my positive error value going up, my negative error value going down from my point, for my uncertainty bars. If I click on OK, then what's going to happen is that my first one, point number 1, has an uncertainty of plus or minus 1. That's how much the bars go up and down. You can see that the second point has bigger bars going up or down. Third one has bigger bars still, and the fourth one has the largest bars. And the last one, the bars go up by 5 and they go down by 5 as well, because I figured out that was what my uncertainty was for my last measurement when I had a x value of 4 and a y value of 42. So I think that's the end of this PowerPoint. I won't click, slide 29 and 29. So that's just what's involved in creating a graph using Excel. So if that's what you want to do as part of your experiment, as part of your scientific report, then that's the way you would go about doing it.